You know, when we think about our bodies, we usually think in terms of biology, right? Organs, cells, DNA. But what if we looked at it from a completely different angle? What if we thought of the human body as a material? Because today, we're going to explore your body as the most advanced, most sophisticated, self-healing material on the entire planet. Okay, let's just start with a statement that sounds completely and utterly wrong. When a young kid named Luca broke his arm, this is what his doctor told him: a broken bone that heals to become stronger than it was before it broke. I mean, how is that even possible? It just doesn't sound right. And that is the big question we're going to tackle today. How can a material not just fix itself perfectly, but actually come back better? The answer, well, it reveals that our bodies are an engineering marvel that human technology is still desperately trying to catch up with. So here's our roadmap. First, we'll reframe the body as a self-healing machine. Then we'll get into the material science of what bone and skin are actually made of. After that, we'll look at nature's built-in repair manual, see how it's inspiring some incredible new tech, and finally, we'll ask what it really means to be a living material. All right, let's jump into our first section, a self-healing machine. And look, this isn't just a cool metaphor. When Luca broke his arm, his body kicked into gear, performing an autonomous repair. That's something engineers would, and do, spend billions trying to replicate in our own materials. And this isn't just about fixing things when they break. The scale of this constant maintenance it's just huge. Your entire skeleton completely replaces itself about every 10 years. Seriously, the bones you have in your body right now are not the same ones you had a decade ago. You're a walking, talking piece of living architecture that's always rebuilding itself. So, how does this living architecture actually work? In section 2, let's deconstruct it, starting with bone. I want you to forget biology for just a minute and put on your materials engineering hat. From that perspective, what is bone? So the key thing to get here is that bone isn't just one thing. It's what we call a composite material. Basically, it's a clever mix of different ingredients that create something way better than any of the parts could be on their own. Think of something like carbon fiber or reinforced concrete. Same idea. And bone's two main ingredients are total opposites. On one hand, you have a hard but really brittle ceramic mineral. It's great at resisting being crushed, but it would shatter pretty easily, kind of like a teacup. On the other hand, you have a flexible, soft polymer called collagen. It's tough and resists being pulled apart like a piece of rubber. Nature's genius was to combine them. And here's the recipe. By weight, bone is mostly that hard ceramic mineral. The collagen fibers act like a flexible scaffold, and the hard mineral crystals grow all around and within it. What you get is this incredible material that's super strong and stiff, but also tough enough not to shatter under impact. It's a perfect partnership. Okay, on to section 3. Let's use that same exact thinking and apply it to our biggest organ, skin. It's not just a covering. It's an incredibly sophisticated, flexible polymer composite, and it's designed for a completely different job than bone. Now, skin uses that same collagen as bone, but in a totally different way. Here, the collagen forms a wavy, flexible network instead of a rigid grid. That's what lets it stretch, and it's mixed with another crucial protein called elastin. You can think of elastin as millions of tiny molecular rubber bands that give skin its amazing ability to snap right back into place. I mean, this comparison is just fantastic. It shows how nature can take the exact same core building block, collagen, and create two materials with completely opposite properties. Bone is engineered to be rigid and resist being crushed. Skin is engineered to be elastic and resist being pulled. It's just a perfect example of nature's genius, using the same simple tools to solve totally different problems. All right, section 4. So we know what these materials are made of. Now let's get to their most amazing trick, automated repair. And this is not a random process at all. It's a beautifully choreographed sequence, like a pre-programmed set of instructions. For a broken bone, it's basically a 4-act play. First, a blood clot forms around the break, acting like a natural internal cast. Then the body builds a soft scaffold of collagen across the gap. After that, special bone-building cells show up and mineralize that scaffold, turning it into a hard lump called a callus. And finally, this is the amazing part, remodeling cells come in and sculpt that callus back into the bone's original shape, often making it even stronger than before. And what's so wild is that when you cut your skin, it follows an almost identical playbook, also in 4 phases. First, clotting stops the bleeding. Then, inflammation cleans up the area. Next is the building phase, where new tissue is created. And finally, there's a long remodeling phase where the new skin gets stronger. It's like there's a universal blueprint for healing built into our bodies. So, all of this brings us to Section 5. The body's abilities are so incredible that engineers are now looking inward for ideas. Instead of trying to invent brand new materials from scratch, they're basically just trying to copy us. And one of the most mind-blowing examples of this is a process called osseointegration. This is like the holy grail for artificial limbs and implants. It's a process where we can actually trick living bone into fusing directly with a metal implant, making that implant a permanent, functional part of your skeleton. So why titanium? What's the secret? Well, it's all about chemistry. First, our body doesn't see it as a foreign enemy and attack it. But the real magic is that when titanium hits the oxygen in our body, it grows this super thin surface layer that our bone-building cells actually recognize. They think it belongs there, and they latch right on, creating a bond so strong that the bone itself is more likely to break than the connection to the implant. And believe me, this is just scratching the surface. We're now moving into an era of truly personalized repair. We're talking about 3D printing a perfect, custom-fit bone scaffold that your body just adopts as its own, or growing large sheets of your own skin in a lab to treat severe burns. This stuff is moving from the pages of science fiction straight into the hospital. It's happening now. Okay, let's pull all these threads together in our final section. What does it actually mean to think of ourselves not just as biological beings, but as living, breathing, thinking materials? This table here really just says it all, doesn't it? The materials we engineer, like steel, are strong, but they're static. They can't heal themselves, they can't adapt. But living materials, they're completely dynamic. They heal, they actually remodel and get stronger in response to stress, and they are in a constant state of renewal, always rebuilding. And that's really the mind-bending takeaway from all of this. We're not just little pilots flying around inside a biological machine. We are the machine. We are the material itself. An unbelievably complex collection of polymers and ceramics that has evolved to grow, to heal, and even to think. And all this leaves us with one last, kind of profound question to chew on. If a collection of simple molecules can arrange themselves to do all this, to heal, to adapt, to become aware of its own existence, what is the true limit, the ultimate potential of a living material? What are we actually capable of?